Good day, everybody, and welcome to the first of a few webinars, actually, that ICsense will host. The first webinar today will be about automotive systems and battery management ICs complying with functional safety. It will be given by our Vice President of Engineering, Pieter de Muyter. If you have any questions during the webinar, you can always send an email to us. We will try to answer the questions afterwards in the last slide. And even then, if we are not able to cover all the questions, please feel free to send them by email to us and we can answer them privately. The webinar will be made available after the session, so we will send you an email, the document with the slides afterwards. So I give the word now to Pieter de Muyter, who will continue with the presentation.
Okay, good afternoon to everybody from my side. As Jeroen explained, today's webinar will be about battery management ICs complying with functional safety. But maybe first, allow me to introduce ICsense. So, who are we? So, we are, in fact, the largest FAB-independent European design group. FAB-independent means that we are free to choose any technology for IC design, so we are not bound to a specific FAB or foundry. Our expertise is in analog, digital, mixed signal, and high voltage IC design, of which you see on the right side of this slide a nice example. Yeah, so a combination of analog design with some digital memory integration combined with some high voltage. So we do everything in-house. Due to that expertise, we are mainly active in automotive, industrial, medical, and also consumer markets. We have two kinds of offerings. So we can do custom IC design services where we design the complete mixed signal ASIC for you, and you can further do the design and supply part, or the supply part. But we can also offer you customer exclusive ASIC design and supply, so where we also do the supply chain management, take the lead in assembly, organize the testing, and so on. We are mainly skilled in innovative, first-of-a-kind ASIC developments. So it means we do new ASIC developments, not fifth generation of same ASIC. To meet this, let's say, to meet our first silicon success rate, we have a unique risk mitigating design methodology. We are also ISO 9001 and ISO 13485, that's medical certified, and we do a lot of developments complying with functional safety standards, ISO 26262 or IEC 61508. Our headquarters is in Leuven, Belgium, and we are founded in 2004. And we are an independent subsidiary from the TDK Group. On this slide, you can see a few very interesting examples of ASICs that we have developed over the last few years. On the top side, you can see a number of developments in the medical market. For example, the 40-channel brain stimulation ASIC, so implantable ASIC inside the brain, cochlear implant ASICs. So that's we have those developments completely in-house. At the middle row, you can see some developments for the automotive sector. You will see there a lot of ASIL-B developments, so developments complying with functional safety. And on the bottom side, there are some industrial or sometimes radiation hard developments that we have done. So you can see a broad range of ASIC developments that we have done. And on this slide, again, a highlight markets that we served. So automotive, where we have done several automotive communication interfaces like CAN, SENT, PSI-5. We have done Hall sensor, GMR sensor interfaces, gyroscope, H-bridge drivers, and so on for the automotive market. For medical, also there, implantable deep brain stimulator ASICs, nerve stimulation ICs, hearing aids, electro readouts ASICs, and so on. We've also done several developments for industrial markets, consumer markets, as well as aerospace. Okay, good. So now let's start with the actual webinar. So first, I will give an introduction why we have today's webinar. Then we will focus on battery management systems, so giving an overview what it is in fact, what are the voltage and current ranges that we are dealing with. And then we go a little bit further into the current sensing techniques, focusing also on different current sensing techniques. And finally, we also focus on a current sensor IC architecture that is compliant with functional safety. Okay, so why did we choose this topic for today's seminar? Well, based on market analysis, it's expected that the battery management system market is growing with at least % every year for the next 5 years. So the market is really expected to expand a lot. And that's not really surprising. If we look to all the trends in car electrification that we have that are ongoing today. One of the big, let's say, trends is the 48-volt board net. So this 48-volt board net enables mild hybrids, as well as it will provide enhanced drivability, so enhanced driving experience for the driver. So having a 48-volt board net together with a 12-volt in the same car, that increases complexity of battery management systems, and it's so for sure one of the reasons why we expect this market to increase a lot. The advantages for a 48-volt board net is that car manufacturers are using this to have a further reduction in CO2, such as start-stop systems, which are now already available for a 12-volt system, but on a 48-volt system, it can be used much more often. Coasting, which means that the clutch is automatically disengaged when the car is, for example, driving downhill. Some regenerative braking, and also weight reduction. Because a 48-volt board net means that the currents in the wiring harness will be less for the same power, and hence which benefits, let's say, for the CO2 emission because the total weight of the car will reduce. In addition, for the 48-volt board net, it can also assist to give a boost in the torque, especially at low RPMs. Some additional features like electromechanical roll stabilization or electrical heated windshield and climate control, they are all, let's say, getting much more popular at a 48-volt supply voltage. Another big trend is, of course, the increasing demand for electrical vehicles. So electrical vehicles, hybrids, plug-in hybrids. So also, these electrical vehicles, they come with a big battery pack, and of course, there also a battery management system is needed. And finally, there is also a large expansion in the ADAS network in a car. So ADAS means Advanced Driver Assistance Systems. And this increasing sensor and actuator network in the car will cause additional fluctuations in the battery loading conditions. And again, therefore, we need more or better battery management systems. So on this slide, I shortly highlight the trends, the advanced driver assistance systems. So these are basically all the systems that help the driver in keeping control of its car. For example, adaptive cruise control, advanced lighting, blind spot detection, collision avoidance, lane keeping systems, and so on. And so, of course, one of the trends, so towards full autonomous driving. So you can see on the bottom of this slide, so there are 5 big levels, let's say, for autonomous driving. starting at no automation at level 0 up to full automation at level 5. And these other systems are there, of course, helping to get up to level 5. Okay, so now let's go a little bit deeper in battery management systems. So what is a battery management system? So in general, you can consider the battery management system as the brain of a battery pack. So on this picture on the left side, you can see in green battery. On the right side, we have some load, which is consuming energy from the battery. We may have a charger to recharge the battery. And in the center, there is the battery management system. So the battery is a big barrel of energy, let's say, and without a battery management system, this can be a dangerous component. If we think about the videos of exploding cell phones, that's of course something that we do not want in our car. So the main tasks of a battery management system is, there are three main tasks, let's say. So it's to protect the battery from operating outside of its safe conditions, to balance the loading and the charging cycles, and to monitor the state of the battery. To do all these functions, the battery management system needs sensors. It needs to detect different parameters from the battery. So there is a current sensor, some voltage sensing, and also a temperature sensor involved in this activity. On the right side, you can see some of the battery state indicators, such as full charge capacity, remaining charge, and based on all these measurements, the battery management system can calculate, for example, state of charge, state of health, and so on. If we go a little further into, let's say, more complex battery management systems, focusing on automotive, we can see that the voltages that a battery management system needs to deal with pretty much depends on the application. So we can go from a regular car with a 12-volt battery up to electrical vehicles running at 400 volt. On the right-hand side, you can see a picture of battery management system for mild hybrids. So we have there a 12-volt battery combined with a high voltage battery at 48 volt, and again the battery management system which is in the center, and it needs to collect all the data, the different current sensors which are available, as well as voltage measurements to deal with, say, with an efficient energy distribution in the car network. Also here you can see on this picture that, for example, electromotors are directly driven from the high voltage, which gives the advantage of additional power, so more functionality can be achieved with this electromotor. Another example here, so a battery management system for electrical vehicles. So I explained on the previous slide, so for a purely electrical vehicle, that voltages up to 400 volt are needed. These are typically comprised out of lithium-ion cells, which have 4.2 volt per cell, and those cells are combined into modules. For example, a possible configuration is 16 modules with 6 cells per module. In this scenario, the battery management system will be distributed. So there will be multiple battery management ICs, for example, one battery management IC per battery module, which are collecting the voltage measurements from each of the battery modules, as well as the temperature. And together with the information from the current sensor, again, the battery management system can manage all the different tasks. In terms of measurement range, if for an empty lithium-ion cell, we have to measure voltages, let's say, down to 9 volt. Depending on the configuration, it can be that one battery management IC has to measure of different modules, which can then, for example, go up to 36 volt. And this whole range needs to be measured with an accuracy well below 1 millivolt. One final example is basically from a regular 12-volt battery management system. I wanted to show this because it's, maybe not everyone is aware of this, that a regular 12-volt in fact has a much wider range. So first of all, you can see the nominal voltage is around 14 volt. And during operation, the voltage can go up to 18, 19 volt or down to 6 volt during a cold start. And even during low temps, the voltage of this 12-volt battery can go up to 40 or 50 volt. So it means that this battery management system has to deal with, again, a wide range, a wide voltage range from 6 up to 50 volt, even for a 12-volt system. Also, reverse voltages are possible, down to minus 18 volt in case of reverse polarity. And things such as microcuts are also possible, so where the battery is for a very short time disconnected, so then still the battery management system has to be able to deal with these microcuts and be able to maintain the overall functionality of the car. Okay, now let's take a look to current sensing ranges. So what kind of current values do we want to measure in a car? So that can go, let's say, from roughly 50 amps up to 500 amps 12-volt system. And for electrical vehicles, these current ranges can go even up to 1,500 amps. So to give you an idea, for a Tesla Model S, when you ask for the full acceleration power, the car will draw 1,400 amps from the 400-volt battery. So these are huge currents that have to be measured, also with quite some accuracy, and we will focus on that later on. Okay, so then we move one step further and we go a little bit deeper into different current sensing techniques. So on this slide, you can find an overview of different possible current sensing techniques. So there is a Fluxgate sensor, there are shunt-based sensing techniques, and there are several examples of magnetic sensor-based current sensing technique based on either a Hall sensor or GMR, TMR. For the magnetic sensors, you will also see there are some differences. Some current sensors use a magnetic core, while there is also a possibility to use open loop or closed loop configurations. So I will talk more about that on the next slide. Maybe what is interesting to see is what are now typical battery management system requirements for current sensing. So for offset requirements, we see typically that the requirement is to be below 0.1 or 0.2% of offset error and gain error below 1%. That includes the full temperature and lifetime drift of automotive development. So temperature range from -4 up to 175 degrees and lifetime more than 15 years. So it's interesting to see that the offset requirement is much more stringent, and that's because measuring an offset current from the battery is very important for a battery management system, as it may indicate that the battery is becoming leaky, and hence there is some potential danger for damage on the battery. Okay, now let's take a look to the different current sensing techniques, starting with the shunt-based current sensing. I would say this is the most straightforward current sensing technique. So we are using a resistor, a shunt resistor, where the current to be measured is forced through this resistor. The voltage across the resistor is amplified and measured with an ADC. There are two different configurations of shunt-based current sensing. That is low side and high side sensing. So on the low side sensing, the shunt resistor is placed between the load and the ground, which is the least expensive and the simplest method for the sensor, but it has as disadvantage that the load of the ground is floating. High-side sensing, on the other hand, requires a more complex current sensor itself. So there is the need for a floating amplifier with a high common mode rejection ratio. And you need to be able to level shift the output of your sensor back to the ground level for further processing. Another quite big disadvantage of shunt-based current sensing is that there is no actual electrical isolation. So you are directly connecting to your shunt resistor, which is carrying the current that we are talking about. So remember, in the range of 1,500 amps. So there is no isolation. There are also large power losses when you are using a shunt-based current sensor. For example, 50 watt will be dissipated in a 50 microohm shunt resistor when there is 1,000 amps flowing through that resistor. And to give you an idea, this 50 microohm, that is really a realistic value for a shunt-based current sensor. So we are talking about resistors in the microohm range. So that imposes quite some system integration challenges, such as contact resistance drift. In the end, we are using 50 microohms to measure a current. So every additional microohm or milliohm that is added is, of course, destroying your accuracy. So that's why you can see on the top right this picture showing a typical shunt resistor for very high current applications. So this resistor has, let's say, a big input part where the large current is flowing through, and there is a small connection which can be considered as the Kelvin contact, so that you can really measure the voltage across the resistor and that you have no influence on contact resistance. Despite for some, let's say, drawbacks, the shunt current sensing is still quite popular because it has quite a good accuracy, and especially there is a low offset because if there is no current flowing through the resistor, the voltage will be zero, hence the sensor itself does not impose offset. The second current sensing technique is based on a Fluxgate sensor. I would say this is the most complex sensor, in my opinion. So a Fluxgate sensor is made out of two magnetic cores, or it can be also one magnetic ring. And this core is driven periodically into saturation by means of this excitation current. Now, when there is no external field present, this BH curve of the magnetic material, it's very symmetrical. So when you're driving magnetic core into saturation, you will see on these pickup on the sense coils, you will see no net voltage appearing. When there is an external field present, it's more likely that the magnetic core is saturated into one direction than in the other direction. And this is detected by the sense coil. This asymmetry is detected by the sense coil, and you will see that voltage difference on the sense lines. By measuring the distance between these sense voltage pulses, it's possible to get a measurement for the external magnetic field. So this sensor has has the best accuracy, so especially a very low offset, but it also comes at a high cost. There are different ways to excite a Fluxgate sensor. So there is a possibility to do a triangular wave excitation, or sometimes we have used a self-oscillating Fluxgate sensor. Okay, then other techniques, other current sensing techniques is based on magnetic sensors. So let me first give you a short introduction into magnetic sensors. So basically, when using a magnetic sensor as a current sensor, we are measuring the magnetic field which is generated by the current that we want to measure. So you can see here are 4 types of magnetic sensors. On the left-hand side, there is the Hall sensor element based on the Hall effect. There is an AMR, GMR, and TMR. You can see that from left to the right, the sensitivity roughly ballpark increases each time with a factor of 10. Yeah. So you can say that the TMR sensor is roughly 1,000 times more sensitive than a Hall element. Maybe I shortly explain you here about this TMR element, because this is quite new technology, let's say, especially in automotive business. So the name TMR stands for tunneling magnetoresist, and based out of two magnetic layers, a pin layer and a free layer. The free layer will follow the direction and the amplitude of the external magnetic field, and the electrons can tunnel through from the free layer to the pin layer through this isolation layer, and depending on the value of the external magnetic field, the tunneling goes better or goes less good. So this will change the resistance which is seen from this point to that point, and hence creating a magnetoresistive. So these magnetic sensors can be used, as explained, for current sensing, and there are two configurations. So we can measure them in open loop or in closed loop. So in open loop, we have here our conductor, which carries the current that we want to measure. There is this magnetic field generated by this current, which is sensed by our magnetic sensor and then further amplified and converted to a digital signal. For this kind of configuration, typically sensitivity and offset error are dominated by the magnetic sensors. So you need often factory calibration or a digitally controlled temperature compensation technique. So these kind of configurations are rather used for low, medium accuracy applications. You can see sometimes that these magnetic sensors are used in combination with the magnetic core, like shown on the picture here on the right-hand side. So this magnetic core focuses the magnetic field lines onto the sensor, which further increases the sensitivity and also reduces the influence of stray fields. One drawback is that the dimensions of this magnetic core have to increase with the current measurement range to avoid saturation. And also high frequency operation can be limited by the losses in this magnetic core. Then we have a magnetic closed loop configuration. So in this configuration, we have again our magnetic sensor sensing the magnetic field. However, when we apply a closed loop concept, we will generate a feedback field which counteracts the external field to be measured, hence making sure that the magnetic sensor is operating around 0 volt conditions. When you calculate a formula, you can also see that based on in this concept, we can get the measured current at the output of our ADC. What are the advantages of closing the loop? So we eliminate the sensitivity variation sensor. So you can see in this final formula that basically only a second order effect is there from the sensitivity of the sensor. There is also an outstanding linearity due to the high gain feedback loop, and the dynamic range is also increased. Main drawback is the increased current consumption due to the feedback current. To generate this feedback magnetic field, you need a feedback current, and that so increases the overall consumption of the sensor. If we put these different current sensing techniques on, let's say, an axis comparing accuracy with cost, we see that on the bottom side we have, for example, Hall sensors, especially then based on open loop configuration. If we move on to a TMR-based solution, including also closed loop, we can, let's say, boost the accuracy quite a lot. And on the top side, you can see here, so Fluxgate Sensor is the most accurate, followed by Shunt-based, but they are both have some drawbacks in terms of cost, module size, power losses, and so on. Okay, now let us take a look at the current sensor IC architecture complying with functional safety. So on this slide, you can see a generic sensor, bias blocks, oscillators. We have some digital controlling system, so some non-volatile memory, some test interfaces, some sequencing. And we have the signal path at the bottom, so amplifying the magnetic signal, converting it with an ADC, having some digital signal processing to do maybe some temperature inputs from a temperature sensor. So further, filtering and linear transformation. And then there is an output protocol, so it can be, for example, a Shunt protocol or an analog output using a DAC and a high voltage buffer. Now, if we want to make this IC compliant with functional safety, let us first see what do we need to do for functional safety. So according to ISO 26262, functional safety means the absence of unreasonable risks due to hazards caused by malfunctioning behavior of electrical systems. So we are dealing with an IC, so an electrical system, and so we need to consider what are the possible malfunctionings. Malfunctioning due to, for example, defects, failures inside the IC. And we want to find a way to avoid unreasonable risk, so to reduce the impact of a failure so that no hazard can occur. So typically you need to do is to control and detect internal failures of the hardware, so of the IC. You also need to control, sometimes detect or tolerate failures external to the element. For example, when the supply voltage drops or when the wiring harness is broken. And you also have to comply with safety requirements of other elements. At the bottom side, you can see what can happen. So first, the IC is in normal operation. Then suddenly a fault happens inside the IC, for example, a short. You get some time, what we call the diagnostic test interval, to detect that a fault has happened. Once the fault is detected, there is still some time needed to react on that fault and to get into a safe state, because the safe state is actually the state in which the IC or the system cannot do any harm anymore. So in this time, from fault until a possible hazard could occur, that's your fault-tolerant time interval. So within that time, you have to detect the fault and get the system to a safe condition. Now let's see, for example, how that may influence our generic IC architecture. So on the green stars, you can see where, in fact, you would need to implement safety measures to detect internal failures. So basically, you need to cover all the blocks which are relevant for safety. So in this example, we focused only on the digital output, so the analog output was not considered. But besides that, you can see that all the blocks have some kind of safety measure implemented to detect specific failures. Now let us take a look at one example from this first amplifier on the next slide. So what you can see here, so we have again our magnetic sensor, which is in this case configured as a Wheatstone bridge. We have here a 3 op-amp instrumentation amplifier architecture for this amplifier, which is then followed by an ADC. So which are possible safety measures for this circuit? One very interesting safety measure is to add some kind of a dummy signal, so on a dummy sensor, let's say, on the ASIC, that mimics a certain sensor signal, and that you can schedule throughout your normal operation, that you from time to time can measure the signal from this dummy sensor, where you know upfront what is the expected output from that dummy sensor, and so it allows you to detect, for example, if there are some offset errors inside the amplifier. You know what to expect, and you compare it with the measured value, in case of large offsets or offset drifts, you are able to detect a failure inside the ASIC. Another example, yes, so this is a fully differential amplifier, which has some kind of common mode feedback circuit also implemented. Yeah. So the next block, let's say the ADC, will only measure the differential voltage, but what would happen if the common mode block, the common mode feedback, gets an internal failure? Yeah. That may lead to a possible wrong measurement, hence a safety hazard. So also for this, for example, it's interesting to implement some monitor to verify the common mode feedback functionality and to flag if something goes wrong in this common mode feedback loop. And as third example, it's always very useful to implement also some kind of out of range detections, which may indicate that either way the sensor or the amplifier gain is, for example, too large, which would cause clipping in the next block in the ADC. So before that happens, you have to detect that the signal is getting out of range. So these are a few examples only for, let's say, this amplifier and ADC. So on the next page, you can see, starting from our generic current sensor IC, which kind of sticks are added to this IC to be compliant with functional safety. So for regulators, we can have, or we have to implement under voltage, over voltage detection. So for each also internal regulator, you have to detect when the supply is getting is bad conditioned. Bandgap and bias blocks typically have redundant circuits so that you can compare one bandgap to another to detect if there is some failure in one of both bandgaps. Oscillators typically come with some watchdog function, also to detect here some frequency getting out of range. Main control systems have CRCs, parities, memories, can have even redundant memories. We covered the amplifier and the ADC part. For our digital signal processing and low-pass filtering, we often implement logic BIST. So logic BIST is, in fact, you can compare it with a scan pattern, but which is then run on the fly during normal operation. So while during your normal operation, you from time to time to launch a test pattern to your DSP and to compare or to check for specific stuck-out faults, for example, in your digital logic. Also some redundancy in a temperature sensor and some specific diagnostics for the send frame for the send protocol are implemented. Okay, maybe one interesting example here that we came across, let's say, in one of our latest developments. So in this case, we have a sensor which provides an analog output signal. So no digital output, but this. And our sensor has to be able to support this kind of safety requirements. Now, the error band is defined as an output voltage which is below 4% of above 96% of the supply range. So when the voltage detected by the ECU is very low or very high, the ECU will know that something is wrong. Now, let's see how that influences the IC design on the next page. For example, here you can see a typical output stage of an IC driving a signal on the line to the ECU. In normal operation, when there is no fault in the wiring harness, the current grows nicely from supply to the ASIC and back to ground. So nothing special, everything looks fine. Now, on the next slide, we'll see what happens in case a ground wire gets broken in the wiring harness. So the ECU implemented a pull-down resistor to be able to detect when something is broken. So the ECU expects that when such case happens, that the voltage will go to 0 volt, so below 4%, and he will be able to detect a failure. However, our ASIC is connected to this line, and you will see that there is still a current path coming through these diodes, through the circuits, through the parasitic diodes, either drain bulk diodes of the output device or some ESD diodes. And in fact, current can still flow through the output pin, through the pull-down resistor, causing a voltage which is above 4%. Hence, with this design and with this IC, it's not possible to detect a broken ground wire. So we do not comply with the safety requirements from the ECU, and we have to find a solution. So on the next page, so you can see here, so a modified output stage design, that with some specific output stage tricks, let's say, and some new ESD concept, it allows to block any reverse current in case of a broken ground wire. So now in this case, when the ground wire gets broken, the current cannot go anywhere. It cannot flow to the output pin. So the ground of the ASIC will float up, and the voltage on the ECU will nicely reduce or get to 0 volt. Hence, the ECU is able to detect this fault in the wiring harness. So this is to give you an idea that sometimes you have to modify your design to comply with safety requirements of other elements. Okay, so we are at the end of this presentation. So let's give it a short summary. So car electrification and expansion in the ADAS network causes a significant battery management system market increase. A battery management system comprises measurement of voltage, current, and temperature in order to monitor, balance, and protect the battery. We have seen different voltage measurement ranges depending on the application. For example, from 6 volt for a 12 volt system up to 400 volt for an electric vehicle with sub-millivolt accuracy. Current measurement ranges can go from several amps up to 1,500 amps, and especially the offset requirements are important for a battery management system, so they must be well below 0.2%. Then we have highlighted some current sensing techniques. So we did some exploration of shunt-based, Fluxgate, or magnetic sensor-based current sensor measurement techniques. We also showed the difference between open loop versus closed loop magnetic sensors. And we gave an overview or a comparison, let's say, between the cost and the accuracy trade-offs for different current sensing techniques. And finally, we have shown, let's say, how functional safety requirements may impact a current sensor IC architecture. So in order to be compliant with functional safety, many diagnostic circuits or redundant circuits have to be added to be able to detect internal failures. And the IC has to be tolerant or comply with different failures in the supply voltage as well as in the wiring harness. So thank you for today's webinar.
So thank you, Pieter, for explaining us the background a bit in battery management IC. So in the beginning, we had this survey asking for people about the experience level, and most of the questions or the answers were low or medium experience. So we really hope that you were able to catch a bit more experience during this webinar. We received quite some questions over email. Some questions came back, so let's try to answer those. We have two questions that came back a few times. The first one is, designing functional safety systems comes with a lot of requirements. So how can you do a good requirements traceability during the design? That's the first question. And the second question is more related to design time and cost. What is the impact of actual functional safety design on the timing of a project and on the cost of a project? So maybe you can try to answer those questions for us briefly.
Okay, thank you, Jeroen. So to answer the first question, referring to requirements traceability. So at ICsense, we have developed a custom requirements traceability system. So we have developed a database system which is let's say, on one hand, takes the ASIC specification as an input together with all the requirement IDs. And on the other hand, we have our simulation environment, which automatically uploads the different simulation results and, let's say, connects them to the different requirement IDs. So we have a full in-house custom requirements traceability system, which then also further, let's say, the database can also be further be linked to our test environment so that we can really have full traceability of requirements from the very beginning to simulation results as well as testing results. And then the second question relating to the impact of functional safety design on timing and effort. Yeah, of course, that's a difficult question. But based on our experience and several functional safety projects that we have done, I would say that roughly an additional timing and effort of to maybe 30% has to be added comparing to a comparable design without functional safety. So on one hand, there are all the additional diagnostic circuits that we need to add to detect the internal failures, but also a lot of additional verification has to be added to verify these circuits are able to deal with different kind of internal failures. And there is also the the more formal part where we have to provide all the necessary documentation and safety analysis to prove in the end that all the work and all the safety measures that you have implemented are actually having let's say a positive impact on the safety of the ASIC, and so to be able to deal with the ASIL requirements.
Okay, thank you for shortly answering these questions. I think we are finished for today. So if any of you have any additional questions, please send them by email. We will try to answer them one-on-one. If you enjoyed the webinar, please let us know, and please join the coming webinar. So the next one will be in June, talking about the decision point, when to go from a PCB to a custom ASIC, when to take that decision, when is there a business case. And the last webinar we have this year will be more in the medical area. So we'll talk about custom ASICs as enabler for medtech, and that webinar will take place in September. So for both webinars, you can register on our website, www.ICsense.com/webinar series 2019. So I want to thank you all for attending this webinar, and I hope you enjoyed it and you can further build on the experience gained today. Thank you very much. Bye-bye.